Hello, I'm Jia-Ju from Tsinghua University. I'm very glad to share our paper about deadlock detection in OS kernels. Deadlocks in OS kernels are caused by locking cycles in concurrent threads. Namely, one thread holds a lock that other concurrent threads want to acquire. Deadlocks are hard to find due to the non-determinism of kernel concurrency. Deadlocks can cause performance degradation and even system halts. There is an example deadlock in Linux BTRFS file system. This bug existed for over 4 years, and it was finally fixed in Linux 5.9. This bug is hard to find because multiple functions are involved and the related thread interleaving is infrequent at runtime. To detect the deadlocks, we need to perform two basic steps. First, we need to extract locking constraints in concurrent threads or code paths. A locking constraint describes the dependency of the held locks and the currently acquired lock. Second, we need to detect locking cycles according to the extracted locking constraints in concurrent threads or code paths. A deadlock can occur in two threads, namely ABBA deadlock, or three threads, namely ABBCCA deadlock, and so on. Many existing approaches use dynamic analysis for deadlock detection, and most of them are designed for user-level applications. Dynamic analysis can achieve low false positives and support deadlock reproduction. However, dynamic analysis requires substantial test cases to achieve good testing coverage, and it also introduces runtime overhead during testing. A typical kernel dynamic tool is LockDep, which has been widely used in the Linux kernel. It performs runtime monitoring and checking based on the granularity of lock class, according to lock dependencies and rules. Some approaches use static analysis for deadlock detection, and most of them are designed for user-level applications. Static analysis can achieve good detection coverage without actually running the program and test cases. However, it often introduces false positives and lacks the support of deadlock reproduction. The sole static approach for kernel deadlock detection is RacerX. It performs flow-sensitive and interprocedural analysis of the kernel code. And then it detects locking cycles as deadlocks. However, RacerX has a high false positive rate of 46%, which limits its effectiveness in practical use. In this work, we aim to design a new static approach of kernel deadlock detection to achieve better accuracy and efficiency. For static kernel deadlock detection, there are three important challenges. First, when extracting locking constraints, it is challenging to ensure both the accuracy and the efficiency, especially when the kernel code is large. Second, when detecting locking cycles, it is challenging to compare numerous locking constraints in lots of code paths. Finally, to achieve better accuracy, it is challenging to drop false positives with short time usage. To solve these three challenges, we propose three key techniques. First, we propose a summary-based lock usage analysis to extract the target code paths containing distinct locking constraints. Second, we propose a reachability-based comparison method to detect locking cycles from locking constraints. Finally, we propose a two-dimensional filtering strategy to drop false positives by validating code path feasibility and concurrency. Now let's see how to extract locking constraints using our lock usage analysis. The first step is to collect target code paths that contain lock-related operations. Our analysis uses a flow-sensitive, field-sensitive, and intraprocedural analysis of the kernel code. It also uses a Anderson-style alias analysis to identify aliased lock variables. To improve accuracy, our analysis creates and reuses function summaries to reduce repeated analysis. It also drops target code paths which contain repeated lock-related operations. There is an example of Linux AFFS file system code. In this example, we find that the functions AFFS free block and AFFS alloc block both call the function AFFS mark SB30. So when the function is analyzed, we create a function summary for it. This function summary stores the target code path and lock-related operations in this function. So we can reuse this function summary when the function is called by other functions. After collecting target code paths, we need to compute locking constraints in each code path. We use a static lock site analysis to handle the cases of acquiring and releasing locks. When a lock is acquired, we create new locking constraints and add the lock in the lock site. When a lock is released, we find and drop the lock in the lock site. With the locking constraints and target code paths, we need to compare them for locking cycle detection. The first step is to identify the same locks in different code paths. In this step, we use a field-based analysis according to data structure type and field. The second step is important, namely comparing locking constraints in different code paths to detect possible deadlocks. The traditional method used by RacerX and other existing approaches is very simple. This method starts the comparison from each locking constraint and compares the current locking constraint with each locking constraint in other code paths. If matched, the method replaces the current locking constraint with the matched one. If not matched, it selects another locking constraint for comparison. Here is an example which contains 4 code paths. Each code path has just one locking constraint. We start the comparison from the code path TP1. The detailed steps are shown in the figure. After the code path TP1 is finished, we start the comparison from the code path TP2. The detailed steps are shown in the figure. From these steps, we find that some of them are repeated, which are shown in bold words. If this repeated comparison can be reduced, locking cycle detection can be speeded up. Based on this idea, we introduce a new structure named indirect locking constraint. It combines multiple locking constraints for a reachable node. The definition is shown in the equation. Let's see the mentioned example again. We still start the comparison from the code path TP1 and add some indirect locking constraints during the comparison. The added locking constraints are shown in bound words. After TP1 is finished, we still start the comparison from the code path TP2. Now we can use the indirect locking constraints in TP1, as shown in bold words, to reduce repeated comparison. Thus, we can find that our comparison from TP2 has less steps compared to the traditional method. We drop false positives from 2 dimensions. The first dimension is to validate the feasibility of each code path by using D3 XMT server. There are 2 stages for validation. When performing log usage analysis for numerous code paths, we perform lightweight and imprecise code path checking to improve efficiency. Specifically, we perform checking in just one function without handling variable assignments, so this checking is imprecise but fast. When checking possible deadlocks, which have fewer code paths, we perform heavyweight and precise code path checking to improve accuracy. Specifically, we perform checking across multiple functions and handle all the variable assignments. So this checking is slow but precise. The second dimension is to validate the concurrency of code paths. First, we check whether the code paths have a common lock. If so, the 2 code paths are never concurrently executed. Second, we check the call graphs of the 2 code paths. If these code paths have common parts in call graphs, they may be sequentially executed at different time points of the same thread. Thus, they are not considered to be concurrently executed. Based on the 3 key techniques, we propose a new approach named DLOS to statically detect deadlocks in OS kernels. We have implemented DLOS with the clone compiler, and it performs static analysis on the LVM bytecode. In the evaluation, we use DLOS to check the source code of Linux 4.9 and 5.10. The evaluation runs on a regular personal computer. We use clone 9 to compile the kernel code with the configuration of all ESConfig. The table shows the detection results of DLOS. We find that by using indirect locking constraints, DLOS reduces much repeated comparison. It also drops many false deadlocks by validating code path feasibility and concurrency. The time usage is less than 7 hours, which is acceptable. In Linux 4.9, DLOS finds 46 deadlocks, and 39 of them are real. 21 deadlocks have been fixed in Linux 5.10. In Linux 5.10, DLOS finds 65 deadlocks, and 54 of them are real. 31 deadlocks have been confirmed by kernel developers. The links of some confirmed deadlocks are listed in the slide. DLOS still has some limitations. First, DLOS has some false positives for several reasons. For example, its field-based analysis can make mistakes when two different variables have the same data structure type and field. Moreover, its alias analysis is interprocedural and flow insensitive, and thus not very accurate. In addition, its code path validation can make mistakes in complex cases, such as array index assignments. Second, DLOS also has some false negatives for several reasons. For example, its bottom-up analysis is not complete when handling call functions. Moreover, it fails to perform analysis of function pointer calls. In addition, DLOS assumes that a code path is never concurrently executed with itself. Finally, let's conclude the work. Deadlocks are dangerous and hard to find in OS kernels. To detect kernel deadlocks, we propose a new study approach named DLOS, which has 3 key techniques. In the evaluation, DLOS finds 39 and 54 real deadlocks in Linux 4.9 and 5.10. We believe DLOS can be extended to detecting other locking issues, such as double locks and using sleepable locks while holding spin locks. Thanks for listening. If you have any question, please feel free to contact us.